Now for section 3.2 on the Baire category theorem. The topic here relates mostly to dense subsets, open dense subsets, and complements of open dense subsets. We've got three little results, the first of which, it's called the nested set theorem, is likely familiar to you for senior level analysis. Check out my senior level analysis 1 notes. There's a link in the online notes to this, in which we state a similar theorem in the real numbers concerning nested closed sets whose diameter goes to 0. So what we're doing is that same type of idea, except here we're doing it in a Banach space. So given a sequence, f sub 1, containing f sub 2, containing f sub 3, of closed non-empty sets in a Banach space, such that the diameter of those sets approaches 0. We defined diameter of a set not so long ago. The claim is there is a unique point that's in f sub n for all n a natural number. We could alternatively state this, and possibly this is how you stated it in senior level analysis, as the intersection of all these f sub n's equals a singleton, a single point, this single unique point. So let's look at a proof of that, really with an eye towards, as we've often done, where the Banach space stuff is used. A Banach space is a complete normed linear space. So where's the completeness used? Where's the convergence of Cauchy sequences used? And it's fairly explicit in this. All right, so we're going to choose x sub n, an element of capital F sub n, so an element of each of these sets. Do that for all natural numbers. You know the diameters of those f sub n's approach 0. You also know those sets are nested in a sense given. Sometimes this is called a decreasing sequence of sets. So for all epsilon greater than 0, there exists capital N, a natural number, such that if index lowercase n is greater than or equal to capital N, if the index is sufficiently large, then the diameter of f sub n is less than epsilon. Simply the definition of the limit of a sequence of real numbers. The limit of the sequence is 0, so eventually those diameters can be made small. No need for absolute values here. Diameters, of course, are non-negative. The f sub n's are nested, so if we look at all m and n greater than or equal to capital N, we choose x sub n and x sub m. Both of these are in a set, say f sub n. I need to know which of these two indices are larger to deal with the nestedness. But the index is sufficiently large that both of these are taken from a set whose diameter is less than epsilon. These are specific elements of such a set. So the distance between them, the norm of the difference of those two elements of that set, must be less than epsilon. So what we've got here is a sequence. These x sub n's that we've chosen form a sequence such that for all epsilon greater than 0, there exists a capital N such that when the indices m and n are sufficiently large, greater than or equal to capital N, we get the norm of the difference less than epsilon. That's the very definition of a Cauchy sequence in a normed linear space. A Cauchy sequence A, Cauchy sequences converge in complete spaces. Banach spaces are complete normed linear spaces. So this Cauchy sequence that we've created, x sub n, converges to some point x. And there's our candidate point that's common to all of these f sub n's. Now, if we look at a particular natural number, lowercase n, and we consider the sequence x sub n plus 1, x sub n plus 2, etc. So we've taken the original Cauchy sequence and just ignored the first n minus 1 terms. We did so we can say this subsequence of the original sequence is a subset of f sub capital F sub n. the index is sufficiently large that all of those terms are contained in F sub n, and the sets are nested. In fact, it's contained in all future Fs as well, all F sub n plus 1, F sub n plus 2, and so forth. But we're getting a sequence in this F sub n set. This sequence, subsequence of the given sequence, or the constructed sequence, that converges to X. So the subsequence also converges to X. Now these F sub n's, they're closed. So if they're closed, then F sub n equals F closure. Closed sets contain limit points. This X that's a limit of this sequence of elements of F sub n must be in F sub n. Closed sets contain limit points in that sense. To be specific, it's given in Theorem 2.2, point A, part 3, where we dealt with the closure of a set in terms of limit points of sequences, or limits of sequences. Since the sets are nested, we actually get this X to be in F sub n for all natural numbers n. All right, so we found an X that is contained in all of the F sub n's, so there exists a point. Now we just need to take care of the uniqueness. Well, suppose there's two such points. Suppose X and Y are both in F sub n for all n. Then the norm of X minus Y, the distance between X and Y, if you like, is less than or equal to the diameter of F sub n. They're elements of F sub n, specific elements, diameters defined in terms of an supremum of such norms, the supremum of the norm of the difference of two elements of the set. This is a specific such number, so the supremum is greater than or equal to that, dissected in vulgar detail. So we've got this inequality holding. This is valid for all n, but the diameter of f of n approaches 0. This is a constant. It's less than or equal to something that approaches 0. So this itself must be 0. The norm of X minus Y must be 0. The only vector with a norm of 0 is the 0 vector. So X minus Y is the 0 vector, or in other words, X equals Y. And that's the uniqueness claim. So there's your unique point contained in all of these F sub n's, contained in the intersection of the F sub n's. Actually, the intersections of the F sub n are, the intersection is precisely the set consisting of point X. I guess we could argue this was kind of constructive in a sense. We found that point X in a very constructive way. Back to the notes. Some comments about dense sets. So the last couple of results concern dense sets and complements of dense sets, duals they call them. If sets A and B are dense in a set X, then the intersection of A and B may not be dense in X. We bring this up because we're going to look at intersections of open dense sets here shortly. But without any extra hypotheses, the intersection of two dense sets need not be dense in a given Banach space, say, or even just a normed linear space, X. Take, for example, X is the real numbers. Take A to be the rationals and B to be the irrationals. The rationals are dense in the reals, the irrationals are dense in the reals, but when you intersect the rationals and the rationals, you get the empty set, and it ain't dense in the reals. So intersections of dense sets need not be dense in general. Turns out when they're open, it's a whole different story. Open dense sets. A note, we'll actually quote this in the proof of the next result. Note 3.2.a says, recall that set Y, a subset of X, is dense in X by definition if Y closure equals X. Definition of dense. Now we know Y closure is all vectors in the space, the big space, capital X, such that for all r greater than 0, a ball centered at X with radius r intersect Y is non-empty. This is theorem 2.2.a part 2. We had also stated something along the lines of it's all points in the space distance 0 from set Y. And that can include, well, it does include all the points in set Y, and it can include some additional points. They must be points awfully close to set Y. They were boundary points, it turns out, which we also said in theorem 2.2.a. So set Y is dense in the big set X if and only if Y intersects every non-empty open subset of X. A non-empty open subset of set X includes a ball of center X and radius R for some sufficiently small r. So such a set must intersect Y, and conversely, since that's what Y closure includes, we get this as an if and only if result. So dense set intersects every non-empty open subset of X. That property we will use in the next result. The following result shows that the intersections of open dense sets are dense. We made a comment above. Well, the intersection of dense sets need not be dense, but if they're dense open sets, then we're good to go. And Baire's theorem, theorem 3.2, says the intersection of, actually countably many, open and dense sets in a Banach space is dense. Okay, we're going to use this idea about intersections with open sets in the proof as mentioned. Let's look at the proof of that. Okay, so let V sub n be a sequence of dense open subsets of the given Banach space. We want to show, sequence means it's countable collection. We want to show the intersection of all those V sub n's is again a dense set in the Banach space. So what we'll do is we'll take W to be any non-empty open set in the Banach space. Then if we can show that there's an element X in the intersection of those V sub n's that's also in the open set, we're showing this set intersect an arbitrary open set is non-empty. It contains something. It contains this X that we're going to find. Then that's sufficient to show that this set, the intersection, is dense in the Banach space. That's what we just said in note 3.2.a. So here's the non-empty open set we're dealing with, and we're showing that this set W the intersection contains something. In fact, we're going to find this something, X. So that's the plan. That's how we'll show the intersection is dense in the Banach space. So first off, we're going to do some inductive stuff here. Open set intersect V1 is open and non-empty. We said the V's were open. The V sub n's are open. So this intersection of open sets is open. It's not empty because V1 is dense in the space. So when we intersect with an open set, we get a non-empty intersection. That was note 3.2.a again. So there's some closed ball, let's call it B1 bar, that's a subset of W intersect V1. Now, hey, W intersect V1, it's open and non-empty. So there's something in it. Being an open set, that something would be an interior point. So we can draw a ball around that interior point, an open ball. Well, take that open ball, cut its radius in half and consider the closure of that. Right? We're talking closed balls instead of open balls here. But once you get the existence of an open ball in the intersection, then we can find a smaller closed ball in the intersection. So we'll find this closed ball B sub 1 closure where the radius of B sub 1 is less than 1. So we can make that radius small. just make it smaller than 1. If there's a ball of radius 7, then there's certainly a ball of radius 1 or less that's contained inside the intersection. Because we've got an open set with the W intersect V sub 1. The openness is playing quite a big role in all this. You see it explicitly right here. All right, so what we're going to do now is inductively create closed balls B sub n bar such that B sub n bar is a subset of B sub n minus 1 intersect V sub n. So we're kind of starting with B sub 0 as open set W. Notice we're dealing with these closed balls. We got our reasons for that. We were just talking about nested closed sets, and we're creating some nested closed sets here. So that's why the discussion kind of oscillates between closed balls, and over here we're looking at open balls. Well, now here we had an open set. Well, we want to continue to do that same kind of procedure. So what we're going to do is look at B sub n minus 1 intersect V sub n. This ball is open, the V sub n is open, and that was the hypothesis. Intersection of two open sets is open. The intersection will be non-empty because V sub n is open, and B sub n minus 1, because V sub n is dense, and because B sub n minus 1 is an open set. The same role that W played up here. Going back to that note 3.2.a. So same procedure. We can create a closed ball B sub n bar of well, let's make the radius less than 1 over n. So we can always, if you can find such a ball must exist. You can make it smaller. So we'll make the radius 1 over n. So these B sub n's are forming a sequence. By the way, notice they're nested. B sub n bar is a subset of B sub n minus 1, the open ball. In particular, B sub n bar is a subset of B sub n minus 1, closure. If you close this off, you've still got a subset of the closure. It's a subset of the open ball, so certainly it's a subset of the closed ball. So the B sub n closures are a nested sequence of closed sets. And by the way, we've made them in such a way that the radius is less than 1 over n for B sub n closure. So their diameters are going to 0 as n goes to infinity. As just stated, the closed balls are nested. So they form a nested sequence. The B sub n closures is a sequence of nested closed sets, and the diameter approaches 0. The diameter of these sets was chosen to be, so we chose the radius to be 1 over n at most. So the diameter is at most 2 over n. But as n approaches infinity, the diameter of these sets goes to 0. So proposition 3.1, the nested set theorem applies. These are nested, a decreasing sequence of closed sets in a Banach space. So there's where the Banach space hypothesis is being used in this one. It's the fact that we required it in the nested set theorem. But we have a decreasing sequence of closed sets whose diameter goes to 0. So there's a unique point X that's in all of those closed balls. So there exists a unique X in B sub n bar for all n a natural number. So X is in W and X is in V sub n for all of the indices. That's because B sub n closure is a subset of W. We kind of treated this as B sub 0 initially. So we get this kind of inclusion. So W includes everything in here, and X is in all of these. So X is an element of W. Also, we chose the B sub n closures to be a subset of the V sub n's, as we saw near the bottom of the previous slide. So all of the V sub n's include all of the B sub n bars, and in particular includes that point X common to all of them. So X is in that open set, X is in the intersection of the v sub n's. It was in the v sub n's for all n, so it's in the intersection. And that's sufficient to show, as we described above, that the intersections of the v sub n is dense in the Banach space. We took an arbitrary open set and showed that it intersects this set, the intersection of all the v sub n's. It intersects it at point x. So by the note we just stated, that means we've got a dense set. So the intersection of countably many open dense sets in a Banach space is itself dense. Back to the notes. Something rather similar to that, let's see here, is the dual form of Baire's theorem. Let's make a quick observation. We'll need this briefly. The proof of the corollary is fairly short. We'll need this comment in the proof of corollary 3.3, the dual form, and let's figure out why they're calling it the dual form. If A is a dense set in normed linear space X, for us in this chapter, it's all about Banach spaces. But if A is dense in set X, then X set minus A has an empty interior, we're claiming. If it didn't, then there'd be some X in the interior of X set minus A, meaning we could find an open ball centered at that X of sufficiently small radius, call it epsilon, that's a subset of X set minus A. And that's the definition of a point in the interior. If the interior is not non-empty, that is, if there's something in the interior of X set minus A, there's a lot of negatives around, even a set minus, then we'd have an open ball. It's a subset of X set minus A. But then A would not have X as a point of closure. If that were the case, because we've got strictly an exterior point there. And so A wouldn't be dense in X. So the claim here is if A is dense in X, then X set minus A has an empty interior. Otherwise, this occurs. And conversely, if the complement of A, if X set minus A has an empty interior, then same argument, A is dense in X. So when we talk about denseness of A, we can talk about empty interior for X set minus A. The dual form of Baire's theorem talks about the complements. So they're using the word dual in the sense of, in Baire's theorem, we talked about open dense sets. Here, we're looking at complements of dense sets and talking about things in terms of empty interiors for the proof. So the dual form of Baire's theorem says, in any Banach space, a countable union of closed sets with empty interiors has an empty interior. Yeah, that's very much with a complement thrown in the right way. That's exactly what we set up here, given this note 3.2.b that links together empty interiors and dense sets. Whereas up here we were talking open dense sets. All right, well, the complement of an open set is a closed set, and we're looking at complements and talking about empty interiors. Complements of a dense set is a set with an empty interior. So the open in Baire's theorem has become the closed down here. The dense up here has become empty interior down here. So we've thrown a complement in there. And the proof is as follows. Take X sub n to be closed sets with empty interiors in the Banach space. So this is the countable collection of closed sets with empty interiors. We want to show that the union of those sets has an empty interior. X set minus X sub n is dense in X because X sub n has an empty interior, as we were just saying in that previous note. So By Baire's theorem, if we take the intersection of all of these, the intersection of x set minus x sub n, then the intersection becomes a union by applying De Morgan's laws. The intersection of x set minus x is the same as x set minus the union. Express it in terms of some complements. I'm sure you're familiar with De Morgan's laws at this stage. But we interchange intersections and unions and move the set minus around. You're effectively doing something with complements with De Morgan's laws. And so what we're showing then is x set minus this countable union, this time, is dense in x. We know that by Baire's theorem, based on the left-hand side. Here we're showing x set minus this then is dense, and that means this has an empty interior. So this union of the x sub n's has an empty interior. Again, it's that note before we stated the corollary. And finally, back to the notes. One passing comment, it's an exercise in this section. So we're really interested in function spaces. The whole Banach space thing is, if it's going to find applications, it's probably going to be when the vectors are actually functions. The text mentions a surprising result about spaces of continuous functions. Exercise 14 states, the set of nowhere differentiable functions is dense in C of 0, 1. This is the linear space of all continuous real valued functions on the interval 0, 1 under the supernorm. So it's a normed linear space. I guess that's all we're stating here. It's a Banach space. And what we're stating is something about a dense subset. That dense subset being the collection of nowhere differentiable functions. Oh, and I think it's surprising because how many nowhere differentiable functions do you know that are continuous? Right? They'd have to be continuous if they're in C of 0, 1. Probably, you know, at most one. There's a standard construction of such a function, but there must be a bunch of them if they actually form a dense subset of the continuous functions on 0, 1. There must be lots of them if they form a dense set. If you've seen this before, you've seen the example. I just need some reference here. Let's go to Munckery's topology book. I have many notes out there on Munckery's topology. I don't have notes on this particular section, not yet at least. Section 49 of Munckery's topology gives a construction of a nowhere differentiable function. If memory serves, I believe it's a construction by Weierstrass to make a function that's continuous, yet it's so bumpy, it's nowhere differentiable. Of course, differentiable implies continuous. So I guess it's a natural question to look in the opposite direction. How badly non-differentiable can a continuous function be? You know, absolute value function's continuous and it's not differentiable, but at one point. Here we're finding functions that are nowhere differentiable. So they must be really, really bumpy, yet they're still continuous. So mildly exotic stuff, and just since we're having a conversation about dense sets in Banach spaces, there's an amusing exercise mentioned in the book. And that takes care of section 3.2. So I will see you soon in section 3.3, and we'll continue looking at Banach spaces. Have a nice day.